Welcome to all on Sethi Lab. Today's session topic is relation and functions plus 2 math. In this session, I'm going to clear the concepts along with illustrations. What is equivalence relation? What is reflexive? What is symmetric? What is transitive? What are the different types of mappings? What is composite function? Each and every topic is being cleared by different illustrations, and each question is taken from NCERT book. This is the very start of the basics of the relation and functions. In the next session, I will discuss further in deeper, right? Now let's start the question. Show that relation R in set Z of integers given by R, A, B, 2 divides A minus B as equivalence relation, right? Before I start the solution question, let's start the concept applicable in this case. What is relation? I have already discussed in the +1 math relation functions in detail. What is relation? Relation is a subset of Cartesian product A cross B. If A and B two are non-empty sets, then relation from set A to set B is a subset of A cross B. Relation on a set. The relation from A to itself is a subset of A cross A. Is called the relation on set A. Example. If A is 1, 2, 3, 4, R is A, B, then A cross A relation is given A minus B equal to 3. Then A minus B is 3. Answer is 3. So in this case, check. 4, 1. This minus this minus this minus this. 4 minus 1 will be the answer. 4 minus 1 is a relation on a set A. Right? Now, what is domain? What is range? And codomain? What is domain? What is root? The relation from set A to set B is defined as A, B belongs to A cross B, then the set of first order elements of the order pairs R is called domain, and set of second elements is called range of relation, domain of relation, right? This is also already discussed in +1 session. You can go through that session also. Domain is set of first elements. It is set of second elements. The set B in the relation R is called codomain. Codomain is this set B. Codomain is set B, right? Next, types of relations. Types of relations, set is called the empty relation. What is empty relation? Word relation of empty or word relation. If no element of A is related to any element of A, then this is called empty relation. Example, let A 1, 2, 3, 8, 10, 11 and R be relation given by A minus B equal to 4. A minus B equal to 4. In this case, you check any permutation combination, we will never get 2 minus 1, 1 minus 3, 3 minus 4. Answer 4 will never be there. Therefore, this is an empty relation. So, since no element A will satisfy the property A minus B4. This is the example of empty relation. Next, universal relation. Relation R on a set A is called an universal relation. If A is related to every element of A, then R equal to A cross A. It is again being created by an example. Let set A is 1, 2, 3, 4 and relation R is given by AB modulus of AB. We can take A minus B or we can take B minus A is greater than 0. In this case, you can see answer is always satisfy the relation. Therefore, it is a universal relation, right? Empty relation, universal relation set are respectively smallest, and this is the largest relation. Larger relation, smallest relation, and they are sometimes also called trivial solutions, right? Next is identity relation. The relation in a set A is called identity relation if each element A is related to itself only and it is noted by IA, right? Then reflexive. Reflexive means ARA. ARA. Relation R in a set A is called reflexive relation A for every A, right? Example. Let A be the set of real numbers. Relation defined by R equal to x plus y equal to A. As sum of two real numbers is also a real number. So R is reflexive, right? Sum of two numbers is a real number, the answer is reflexive. Symmetric. Symmetric में क्या होगा? If A are B, then B are A. If A are B, then B are A. Then it is symmetric, right? Now let's example. Let A be the set of even natural numbers. And relation that is defined as x plus y is divisible by 2. Sum of two even natural numbers is always even and hence divisible by 2. So it is suppose 2 plus 4 divisible by 2. Correct? Then 4 plus 2 will also be divisible. This is ARA, this is BR. ARB, this is BRA. Right? So this is a symmetric relation. Next is transitive relation. Transitive में क्या होगा? If ARB and BRC, then ARC. If this condition is satisfied, then the relation is transitive relation. Example, let us a set of positive integers defined known as, in this case it says 2 is greater than 4, 4 is less than 6, then 2 is less than 6. Relation is less, right? So this is the positive natural positive integers. This is ARB, this is BRC, this is ARC. Generalized way, this can be written as x less than y less than x will be greater than for every A. Therefore, it is transitive relation. Identity relation is always reflexive, symmetric, and transitive. Now, equivalence relation. Equivalence relation is that relation which satisfies the condition RST. RST means it should be reflexive, S for symmetric, T for transitive. Right? Now let's start the question. Question is, A minus B divided by set on integers. Set of integers. Set of integers. Integers means -3, -2, -1, 0, 1 like this. All the positive. Set of integers. A minus B. 2 is divisible by A minus B. 2 divides A minus B. 2 divides A minus is divisible by A minus B. B minus C is B minus C is for reflexive. For reflexive, we take A minus B. A minus B is, for reflexive, we consider ARA. ARA means A minus A equal to 0, which is divisible by 2. For symmetric, if A minus B is divisible by 2, then B minus A will also be divisible by 2, right? As no, therefore it is symmetric. It is symmetric. Next, black. For transitive, if A or B, A minus B is divisible by 2 and B minus C is also divisible by 2. Then to prove for transitive, A minus C is divisible by 2. Say this is 1, this is 2. So 1 plus 2 will be A minus C will be divisible by even number, that is 2 also, the one 2 also, right? Therefore, transitive, given relation is transitive also. Now as relation is reflexive में क्या होता है AR, symmetric में क्या होता है if AR B then BR A, then transitive इसमें क्या होता है if AR B and BR C then AR C. As all these conditions are satisfied in the given relation, therefore relation is an equivalence relation. I can explain with this 2. 2 minus 2, 0, divisible by 2, 0. 4 minus, if A or B, 4 minus 6, divisible by 2, A or B, 6 minus 8, divisible by 2. If we add 2, 4 minus 8, that is minus 4, divisible by 2, right? Just what give more impressions, right? Now, I think this question will be clear. In this case, question was A minus is divisible by 2. We have to prove that relation is an equivalence relation. To prove it, we have to show the 3 things. It should be reflexive. Reflexive means ARA, right? Divisible by symmetric means if ARB then BRC. Transitive means if ARB and BRC then ARC, right? Therefore, now I will start the next question, that is a one-to-one on-to-into functions, right? Let's start it. Now, the next topic I am going to discuss is different types of mappings, or you can say functions. There are 2 questions. Show that the function end-to-end given by fx equal to x is 1, 1 but not on 2. And second is prove that function r to r given by fx equal to x is 1, 1 and on 2. Now, before start of the solution of these 2 questions, let's clear the very basic concepts, right? What is 1, 1 function? If each element in the domain of a function has a distinct image in the codomain, the function is said to be 1, 1. One functions are also called injective function. This is an injective function. If it is not 1, 1, then it is many-one. Methods to find. There are number of methods. But here I will discuss only one method, and remaining will be discussed in the another session. Right? In this case, take x1 equal to x2. If finally take fx1 equal to fx2, and if finally on calculation we get x1 equal to x2, then it is 1 to 1, otherwise, right? Then if take fx1, this is fx1 equal to fx2. If finally on calculation we get x1 equal to x2, then it is injective or 1 to 1 function, otherwise it is many-one. Another method I will discuss in the another session. Example, fx equal to 3x is 1 1, r to r. Be very careful on this issue. In this case, take fx1 equal to fx2, that is 3x1 plus 5 equal to 3x2 plus 5. This is goes x1 equal to x2. Therefore, it is 1 more injective function. In this case, this is r to r. In this case, x1 square plus 1 equal to x2 square plus 1 on function x equal to plus minus x2. That is not 1 1, right? Now, in the note is given, a function will be either 1 1 or many-one. Another method, lines drawn parallel to the x-axis from each corresponding image. Points should intersect the graph y equal to fx at one and only one point. Now let's example here. This is the graph given 3x plus 5. We draw the line, right? We draw the line y equal to fx. Y equal to fx. These are the lines parallel to x-axis, right? If each line intersect at only one point, then it is 1 1 function injective. If it intersects more than 2 points, then it is not 1 1 function. This is the graphical method. Graphical method. Right? The manual function is made one by restricting the domain of the original functions, as in case of inverse trigonometric functions, that I will discuss in the chapter inverse trigonometric function, chapter 2 plus 2 mathematics, right? And second function was y equal to x square plus 1. This is the parabola like this. If you draw a line parallel to x-axis, draw a line parallel, point of intersection, one is this, one is this, one is this, one is this. Means more than one line intersecting point, then this is many-one. This is many-one, right? Next. Onto and into function. Onto another name is surjective. F x to y be function if each element in the codomain y has at least one pre-image in the domain of x. Each element means, suppose this is given to you 1 2 3 4 5. This is. In this case, no element should be unoccupied. If no element is pending, yani every element is occupied. Another way, no element should be unoccupied. Suppose this is x to y. Then is onto, if element is pending, unoccupied, then it is into. In this case, into में क्या होगा? Suppose like this. This is 1 2 3 4 5 6. This is occupied, this is occupied, this is occupied. Now this is 6 is not occupied. Not occupied. This is pending. Therefore, this is into. This is into. This is onto. Now, again repeating. Surjective. Let f(x,y) be function if each element in the code has at least one pre-image. In the every element, this is a pre-image, this is pre-image, this is the image. So, y has at least one pre-image in the domain of x, every element, each element. In this case, 6 has no pre-image, therefore this is into. This is clear? What is onto? What is into? A function, bijective function. Bijective function is that which is both one to one and on to. That is called bijective function. Right? No, this is not required here. A function will be either onto or into. This will be either onto or into. Now, let's start the question. Question is, show that function is 1, 1 but not onto. Now, I have selected these questions only due to give the importance of this. Give the importance of this. What is the importance of this? This is n to n, natural number. This is real numbers. This is natural numbers. Natural numbers. Right? If we take here 1, 2, 3, we will get 2, we will get 4, we will get 6. In this case, 1, 3, 5. 3, 5 will remain unoccupied. Will remain occupied. Therefore, it is 1 to 1, but not on 2, because in this case, these elements remain occupied. Clear? So, on to means not on to. Not on to, on to. Reason? Instead, in this one, elements remain unoccupied. Right? In this case, if we take here, this is R. If we take 1, we get 2. 1, 2. If we get every element we can take here. In this case, because it is R to R, this is R to R. Then if we take F1, we get 2. If we get 0.5, we get 1. Right? In this case, 1 was not available. In this case, similarly, we get every element. It means will be occupied. Occupied, therefore, on to. 1 to 1, right, and on to. 1, 1 and on to both. If this is 1 to 1 and on to, this is bijective also. So be careful, R2 R hai, N2 N hai, R2 N hai. Accordingly, we have to decide. Right? Now, I will next start the composite functions. Let's start composite functions. Now, we will start the topic composite function. Question is, consider f n to n, n to n, n to r defined by fx, 2x, dx, cy plus 4, x is sin z, such that x, y, z, and n. Show that h o g f equal to h o g f. This is the composite functions. Composite functions, and to prove that composite functions are associative. Associative. Composite functions are associative. Now, before I start with the question, let's discuss certain concepts applicable. This is A to B, B to C. This is GOF. This is GOF. Now, we will start with certain things. Suppose fx is 2x and gx is x square. F1 is 2. Fgx is 2 into gx whole square, that is 2 into x square whole square, that is 2x to the power 4. This is FOG. Simple. In the function, replace x by the another function, that is the composition of function. This is a very basic. Now, a to b and b to c with two functions, then g of f is a to c. This function is called the composition function f and g and given by g of f, that is in the function g replace x by fx, x belongs to a. Properties of composite function. Properties of composite function. The composition function is not continuous in general, not commutative, It is associative. I am going to prove this question also. Composition of any function, where any function is the function itself. These are very important for the entrance point of view. A to B, B to C, 1 1, then G of is also 1 to 1. A to B, B to C are on 2, then G of is also A to C is also on 2. GF is 1 1, then fx is necessarily 1 1, but gx may not be 1 1, right? Now, these are the properties. Certain things to be discussed here. Here is given, consider the function fx and gx. This function is 1 1 and on 2. And this function is many 1 and into. On to this function is many 1 into, as two elements remain unoccupied. This is onto, as all elements are occupied. Now, in this case, it is saying gfx is 1 1. How to find it out gx1? I am saying gf1. gf1 will be, f1 answer is 1. g1 answer is 1. That become 1 1. gf2. G2, this answer is 2. This answer is 2. This becomes 2 2. GF3, that is G3. G3 answer is 3. This comes out to be 3 3. Similarly, GF4, G4, this comes out to be 4 4. So this comes out to be GF is 1 1, right? Now, similarly, in this case, we can say F is, this is many 1 and into, as element is unoccupied. Okay. This is many 1 and onto, as all elements are occupied. This element is unoccupied. In that case, GF1 is 1. F1 is 1. This is 1. This comes out to be 1 1. GF2, G2, this comes out to 2 2. Similarly, G3 is 3, 3 is 3. This comes out to be 3 3. Similarly, 4 is 3, 3 is 3. 4 is 3, 4, 3. These are coming answers. So F is into and G is on 2. but GF is on 2. GF is on 2 because every element is being occupied. Right? Now, let's start the question. We have to solve the property of left hand side. We pick up left hand side. Left hand side. H G O F. To find it out, first we find G F X. G function G is 3 y fx plus 4. This comes out to be fx is 2. So 3 into 2x plus 4. 6x plus 4. Now H O G O F, that can be written as H in the function H G O F, that is sine x. Sine z can be represented as sine of 6x plus 4. Right? This is equation 1, left hand side. Similarly, right hand side, HOG. First find HOG means HGX. HGX. Function H is sine. G is 3y plus 4. Therefore, HOF OF. In the function, put sine of 3 into 2x plus 4. This comes out to sine of 6x plus 4. Right? This is equation 2 as 1 equal to 2. Therefore, proved and associative property is proved. Associative property is proved. Right? Now, I would like to discuss. If you are new to my YouTube channel, Sethi and like this video, please subscribe and share the channel. Press bell icon to receive updates on upcoming concept clearing videos. Concept clearing videos. Thank you.